We're now going to take a look at hydrostatic forces on submerged curved surfaces. So we've already looked at this on planar surfaces, and for that we came up with a series of equations. And the way that we did that is we went through an integration procedure. And so we could do that integration again. However, it'd be a little complex. This is what would be involved. So this was the equation that we integrated when we were looking at planar surfaces. And for planar surfaces, the area was kind of easy. When we're dealing with curved surfaces, we could have a much more complex surface. And consequently, it can be a little bit on the laborious side. And as a result, what we're going to do, we're going to look at a bit of a shortcut. And that's what we'll talk about in the next two segments. So to begin with, what I'll do is I'll draw a schematic that we'll be referring to as we go through the derivation. Okay, so this is the curved surface that we're dealing with, and we're trying to determine the forces on the curved surface, which is submerged below the surface of some liquid. And what we're going to do, we're going to simplify matters by creating this chunk of fluid that is above the plate, and we'll say that on the upper surface of the chunk of fluid we have a force Ft. There's a force acting on the left-hand side of the fluid, and that will be at the center of pressure of this surface AC. This is the center of area of AC. And we're going to go through and use this schematic as the starting point for our analysis. And the way that we're going to begin the analysis is we're going to sum forces on the fluid mass ABC. So that will be the chunk of fluid that is essentially right in here inside of this area that is drawn out with the curved surface. And when we sum forces, we equal them to 0. So what we will do, we'll begin by summing forces in the y direction. So the y direction looking back at our schematic in the y direction, what do we have? We have this force, we have the weight, and we have Fry. And those all equal 0. And for the force on the top, that is going to be this depth, H1, and that will give us the hydrostatic pressure multiplied by the area, and the area there would be CB. So this is assuming unit depth that we're looking at, and that's why we've defined that as being ACB. And with that, we can write Fry. So this is the hydrostatic pressure at the top of that surface CB multiplied by the area plus the weight of the fluid element itself, which is in the curved surface. That gives us Fry. So that is the force in the y direction. Now what we're going to do, let's take a look at the force in the x direction. And the forces involved here is going to be the hydrostatic force here at the center of pressure. As well as the reaction force. Now, the hydrostatic force is going to be the pressure at the center of area of AC. There's our diagram. So it's going to be of this area here, AC, where A and C is there. So with that, we can write out the force, the reaction force in the x direction. And here, H, that's the center of area of a surface AC. And one thing that we can note, we have pressure atmosphere here. If it turns out for our particular system that we're looking and we have P atmosphere out here, we can neglect that atmospheric pressure from the equation that we have. Okay, so there what we have is we have an expression for FRY and we have an expression for FRX. For right now, however, we're not really sure where those are acting, and in order to figure out where they're acting, just like when we looked at planar surfaces, what we had to do, we had to go through and sum moments, and so that's what we're going to do in the next segment. We're going to sum moments in order to figure out where those forces are acting on the curved surface.